Hello and welcome to this video on how to fit classical test theory measurement models in Mplus. My name is Geiser, I'm an instructor with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about multivariate statistical methods including factor analysis, structural equation modeling, multi-level modeling, latent class analysis, and also about psychometric topics including classical test theory methods and item response theory. In this video, I want to show you how to fit the different measurement models from classical test theory in the Mplus software. And you can do this in pretty much any software for structural equation modeling, including Mplus, Lavaan, AMOS, EQS, Literal, and all the other programs, because models of classical test theory are confirmatory factor analysis models with special constraints. And so really any program that can do confirmatory factor analysis will allow you to do this, including point-and-click software such as JASP, for example, could also be used at least for certain types of factor analytic models. Now, Mplus has great flexibility for doing this with various types of estimators and with just a few commands. So I'm going to show here how this is done in the Mplus software. And I'm going to start with the simplest classical test theory model that is called the strictly tau parallel model. I'm going to show you how we can fit that model in Mplus and what the parameters are that you should look for and how this model could be relevant to your work when you develop a new test or when you evaluate the reliability of a test that you're using in your research. So let's go take a look at the syntax here. You can see in my example data file ctt.dat. I have four variables y1 through y4, and here for the strictly parallel model I'm going to focus on just two variables to show you that even with just two test score variables, a model of strictly parallel tests can already be identified and leads to an over-identified confirmatory factor analysis model. That's one of the frequent misconceptions about classical test theory that some people have, according to which classical test theory models are not testable. So many people think that this is a downside of classical test theory, that it makes untested assumptions and so therefore it shouldn't be used, but that's actually not true. All measurement models of classical test theory can be tested provided you have enough data. So for the strictly parallel model, that means having at least two test score variables is sufficient. We'll see later that for other classical test theory models, two is not enough to have an over-identified testable model, but here for the strictly parallel model, that is sufficient. By the way, if you want to know more about classical test theory measurement models and classical test theory, check out my playlist on this channel for classical test theory and reliability estimation, and also I have a separate video where I go over each one of these measurement models in more detail in a separate video, so check that out as well. So let's go ahead and take a look at our model statement here. You can see that I'm specifying a common true score variable or factor in the sense of confirmatory factor analysis here by specifying tau is measured by y1 and y2. And notice that unlike a conventional factor analysis model, both of the factor loadings here have to be fixed to 1. And so if you had more variables in your model, then all of these would have to have the @1 at the end in the by statement so that Mplus knows that all loadings are fixed to 1. That's one implication of the strictly parallel model, that all variables have the same loadings, the same factor loadings, and we can simply fix them all to 1. Next is a specification of intercepts, which Mplus adds by default. When you run a confirmatory factor analysis model, intercepts or additive constants are added to the measurement model. And in the strictly parallel model, there are no intercepts. So the variables all are assumed to have equal means, meaning there's supposed to be equal scale difficulty under this model. And so all intercepts have to be fixed to 0 because there's only a common mean. The model implies that there's one and only one common mean, true score mean, that that applies to all test score variables, and that mean will be estimated in a separate step, but there will be no intercepts for the observed variables because the observed variables are not allowed to differ from that common true score mean. So that's another thing to remember, is for all variables that you include in your strictly tau parallel model, the intercepts have to be fixed to 0. Now let's take a look at the free parameters in the model. And so you can see that 1 is the true score mean, so the mean of the common factor, which is estimated, and that represents the common mean that applies to all variables under this model, assuming that the variables have equal difficulty. Also, the true score variance is estimated using this command. And that's a key parameter of interest because the true score variance allows us to determine the amount of true inter-individual differences between people. So this is the variance component that reflects true differences between people as opposed to measurement error differences, which are also estimated. And that's the last command here in the model statement, y1 through y2, and a label in parentheses r var, so error variance, and shows that label. And so what that does is it allows the error variances to be estimated. However, they have to be set equal. They have to be estimated to be the same for y1 and y2, which is another implication of the strictly tau parallel model of classical test theory. So this is a very restricted confirmatory factor model with a single factor, equal loadings, equal intercepts or 0 intercepts, and equal error variances. And so only only 3 parameters are estimated here, regardless of the number of observed test score variables that you include. We only have the true score mean as a free parameter, the true score variance as a free parameter, and the common error variance, which is equal across all variables included in the model. Now let's take a look at the output file for this model. So let's run this and take a look at what Mplus gives us for this model. When we scroll down here, we can see that we get the observed sample statistics, the means, and you can see the means here are relatively different, 35 versus 33. We have the covariance matrix with the variances in the diagonal. You can see also the variances are a little bit different. The first variance is a little larger than the second variance, and the variables are substantially correlated, 0.628, which is expected for variables that are supposed to measure the same common true score variable. They should be strongly correlated. Otherwise, it would be strange if they weren't highly correlated and they're supposed to measure the same construct. That would not be expected. The model fit looks bad. So when we take a look here at the chi-square test of model fit, you can see the model is over-identified, even with just 2 test score variables. So it is a testable model, has 2 degrees of freedom, and those 2 degrees of freedom come from the restrictions on the error variances and on the intercepts. So remember that this model assumes 0 intercepts and that there's a common mean, and it also assumes that the variables have equal error variances. And so then that constrains the observed means to be equal, and it also constrains the observed variances to be equal. And so if any one of these constraints are not in line with the data, then the chi-square test will show this, provided it has enough statistical power, meaning if you have a large enough sample size, the chi-square should detect any misfit or any differences in the observed means or any differences in the observed variances beyond sampling error. And so here you can see that the chi-square is showing us there's a problem here. So either the means are not the same or the variances are not the same, or both. So both could be violated, and so that's for us to find out. So this model does not fit. Let's nonetheless take a look at the parameter output, and you can see here that what is estimated by Mplus is the common true score mean, and it's somewhere in between the observed means, obviously, to maximize the chance of adequate model fit. So that's the common mean that would apply if the variables had equal means in the population. And then also there's the true score variance component estimated, and there are the 2 residual variances, and you can see they're exactly equal because of the equality constraint. So really this is only one parameter that is estimated, has the same standard error and test statistic, and so there are really only three parameters that are estimated in this model: the common mean, the common true score variance, and the common error variance. In the standardized solution, we can see that the factor loadings, the standardized factor loadings are 0.77, so relatively large. We will see later that the squared standardized factor loadings equal reliability in this model, or R squared. Also, you can see that the standardized residual variances are 0.405 each, and so that's the amount of unreliability. So that is 1 minus reliability, or 1 minus R squared in Mplus. So 40.5% of the variance in the observed test score variables are due to error variance, so measurement error. So that's a relatively high amount of measurement error in these test score variables. The remaining 59.5%, which are given by R squared in Mplus, are reliability. So that's true score variance. So about 60% of the variance is true score variance, and about 40% of the variance here is error variance. Notice that under the strictly tau parallel model, the variables have equal reliability. So that is one feature of the model that is nice. When you have strictly tau parallel variables, then they have equal, you can assume that they have equal reliabilities. Now, problem is here that this model didn't fit. So we can't really trust these parameter estimates or any of the estimates under this model. And so we need to figure out what's going on here. And one thing that can help us is to look at model residuals, where we can see any discrepancies between the observed means and the model implied means, as well as between the observed covariance matrix and the model implied covariance matrix. And so you can see that as expected, the model estimated means are equal. So under the model, the means have to be equal, yet in our data, we saw the means were not equal. And the question is this inequality of the means due to sampling error alone, or is there a significant difference between the means? And you can see that the standardized residuals for the means here are fairly large. So those are z-scores, and one z-score is about 6, the other one is -9. So in terms of an absolute value, that's also large. So -9 or -9 is a large z-score, which would be significant, statistically speaking. And so this means that there's a significant discrepancy between the model estimated means and the observed means in our data. So those residuals are substantial. So that could be a reason for model misfit. Also, when we take a look at the model estimated covariance matrix, you can see that this model implies equal variances because you have the same variance here in the diagonal for both variables under the model estimated covariances. And again, when we look at the residuals, you can see those are fairly sizable in terms of the absolute values. So there's also a potential problem with the assumption of equal variances, which may not be met. Now, one thing that we can do first is we can look at what happens if we relax the assumption on equal means. And so that turns this model of strictly parallel test score variables into what we call a model of essentially parallel variables. So we would not give up the assumption of equal error variances, but we would give up the assumption that the variables have strictly equal means, which could be reasonable. If they differ in their difficulty, then it may be reasonable to give up that constraint on the equal means. And the way we do this is by keeping only one of the intercepts fixed at 0, for example, the one of the first variable, and then freely estimating the second intercept by taking away the at 1 and putting a star instead. And so then we are now estimating the second intercept instead of keeping them both fixed at 0. And what that does is it allows the mean of the second variable to deviate from the common mean, because it gets this additive constant that then indicates the mean difference relative to the first indicator. And so that's then a meaningful way to assess mean differences and allow for mean differences between the different scales. Now the other parameters remain unchanged, so we're adding one parameter to the model by allowing this intercept. So we're making this model a little bit less restrictive by adding in this intercept for the second variable, which is now freely estimated, but the error variances are still constrained to be equal. And also we're only estimating the true score mean and the true score variance as additional parameters. So this model then has 4 parameters: the intercept, the true score mean, the true score variance, and the common error variance. Let's take a look at how that turns out for our example. And let's take a look at model fit here real quick. You can see the chi-square is now much better. So now it's only 3.747. Previously it was 50 something. And we have 1 degree of freedom less because we are estimating 1 additional parameter. So rather than having 2 degrees of freedom, this model has only 1 degree of freedom, but it's still over-identified because it still constrains the variances to be equal across the 2 variables. And so that's still a testable assumption. And you can see the p-value here is borderline, so 0.05. So strictly speaking, we would still reject the null hypothesis that the model fits exactly in the population. However, this looks much better than the previous model. The RMSE is still a bit high. CFI and TLI would indicate that this model is okay. And SRMR is not so great. So it's debatable whether the assumption of unequal means is sufficient for model fit. So maybe we also need to relax the assumption of equal variances. And we can check on that in a little bit. So let's first take a look at the parameter estimates here. And you can see that now we have an additional parameter under intercepts. And so that is the intercept, negative 2.264. And you can see it's statistically significant, which means it's different from 0, which indicates that the 2 scales differ in their difficulty. And it's statistically significant. You can see that when you go to the observed means, you can see the second scale is harder. So the second test that's used here has a mean of only 33, whereas the first one has a mean of about 35. And so that about 2-point difference between the means is now exactly reflected in that estimate of the intercept. And so the intercept gives you the mean difference between the first scale and the second scale and indicates that the second scale is more difficult, and that is significant because the p-value here is very, very small. So there's a significant difference in test difficulty between those 2 tests, and that's one interesting finding here, or one relevant finding when using this essentially parallel model in Mplus, and tells us that we have tests here that differ in difficulty. When we look at the standardized parameter estimates, we can see that still the variables have the exact same standardized loadings and the exact same standardized residual variances, which is the case also in the essentially parallel model, since the variances are still constrained to be equal. And so you can see the reliabilities here under this model are estimated to be a bit better. About 63% of the variance according to this model is true score variance, and about 37% of the variance is measurement error variance. So this may be a bit more accurate because this model fits better than the previous strictly parallel model. So perhaps those reliability estimates are a bit more trustworthy. Now, we still saw that this model was borderline acceptable in terms of the chi-square. The p-value is 0.05 exactly, where we would still reject the null hypothesis of model fit if we were strict. And so let's take a look at the residuals one more time. You can see now that the restriction on equality of means is now gone. So the model estimated means are no longer equal, and as a result the residuals for means are 0, because now the mean structure is exactly reproduced, or we could say the mean structure in this model is saturated. So there's no restriction here on the means, and so therefore the residuals here are 0. However, there's still a restriction on the covariance structure, and that is the restriction of equal variances, as you can see here. So these variances, 64.10, those are the model implied variances, and they are equal for y1 and y2, and that's still a constraint in the model, and that could be wrong based on our observed data where the variances may differ. And so you can see that the residuals here for the covariances are 4.47 and negative 4.47, and when we look at that in terms of a z-score, you can see that this one's still pretty sizable in terms of an absolute value for a z-score. So perhaps, so say it's also the case that the variances are not equal, that these variables are not essentially parallel. So what could we do then? So if that's also the case, what would be the next step? So the next step could be to relax that assumption as well. So rather than constraining the error variances to be equal, we may decide to freely estimate them. And so then they would no longer be set equal. So error variances not set equal. And so this then turns the model into what we call a model of essential tau equivalence. With essential tau equivalence, the variables still have equal loadings. However, they can have unequal intercepts, and they can also have unequal error variances. And then that's called essential tau equivalence, where we no longer require the variables to have equal variances or equal means. They still have to measure the same true score variable or common factor with equal loadings, but they're not required to have equal means or equal variances. And so let's take a look at how this model fits these data. And let's go right down to the chi-square test of model fit. And you can see, oh, now we have no degree of freedom left. So this is a saturated model when you have just two variables. And as a result, the chi-square value is 0, and the p-value here should really be given as 1.0, because this model must fit perfectly by definition, because it's a saturated model. And that's always the case when you fit an essentially tau equivalent model to two variables. This model will always be saturated. Now, if you have 3 or more variables, then the model would be over-identified, because it still has a testable constraint on the covariances. So with 3 or more variables, you have multiple covariances in your data, and under essential tau equivalence, all covariances have to be equal in the population, and that would be testable with more than 2 variables. However, when you have just 2 variables, it's not testable and the model is saturated. Nonetheless, you get parameter output and it's interpretable. So this may be the only model that you may be able to use. If the other 2 are rejected, you may have to go with essential tau equivalence, and this may still be useful because you still get an estimate of the true score mean, which is the mean of the first variable in this case, which was used as reference here, where the intercept is 0. And then the second variable has the intercept, which again tells us about mean differences. So this shows us again that the second scale was more difficult than the first scale. And we get an estimate of the true score variance, and we get estimates of the error variances, which, as you can see, are now allowed to differ. So under essential tau equivalence, the variables can have different reliabilities, and that may be useful because perhaps you may not be willing to assume that the tests have equal reliabilities. Let's go down to the standardized solution, and you can then see that now also the standardized loadings differ as a result of having unequal error variances, and the residual variances differ again, obviously. And then down below you find R squared, which again can be interpreted as reliability. And so now the reliabilities of the 2 variables can differ. And so the first variable has a reliability according to this model of 0.586, which means for the first variable, 58.6% of its variance are estimated to be true score variance. For the second variable, 67.4% of the variance are estimated to be true score variance. So according to this model, the second scale would be more reliable than the first one. Now, those are three models of classical test theory that we can fit with just two variables. There's one other one, and that's the model of tau equivalence. So right now we were looking at essential tau equivalence, but there's also a model of strict tau equivalence. Strict tau equivalence takes away, again, the freely estimated intercept. So if you wanted to do a model of strict tau equivalence, you would again set both intercepts equal, or set them to 0, like we did in the strictly parallel model. So this would be a tau equivalence model. Now here again, we already know that this cannot fit because we already determined previously that a model which assumes equal means between the two variables didn't fit. So we don't have to do this strictly tau equivalent model because we already know that it won't fit the data well, but just in case you want to fit it, this is how it's done. Now, there's one more model of classical test theory, and that is the tau congeneric model. The tau congeneric model is a very general measurement model that we frequently use in confirmatory factor analysis and structural equation modeling. And that model allows variables to not only have different means, but also it allows variables to be measured in completely different units of measurement. So for example, if you had multiple temperature scales for measuring temperature and you thought that they were maybe partly unreliable and you wanted to do a classical test theory analysis with them, then one scale maybe in Fahrenheit units, another scale maybe in Celsius units, and another one maybe in Kelvin units or something like that. And so then the congeneric model would allow you to still view these measures as indicators of a common factor because it allows factor loadings to differ between different scales. Now, a congeneric model cannot be fit with just two tests unless you have other variables in the model that are correlated with the factor, with tau. So if you add an observed variable that is correlated with tau, or another latent factor that's correlated with tau, then it is possible to have just two variables where the loadings are different. But when you look at this factor in isolation, so when you have only tau and you want different loadings, then that is not identified unless you have at least three variables. With three variables, a single factor model with unequal loadings is just identified or saturated, and so you need at least four variables for that model to be over-identified in isolation, meaning without other variables that are correlated with tau. And so let's do one here with four variables. So I'm going to add the other two variables to my use variable list by stating use var equals y1 through y4, and then I'm going to put them all here, y1 through y4. Now I don't have to say anything about the loadings because Mplus will automatically fix the first loading to 1 for identification, and the other loadings will be freely estimated. So that makes it really easy to specify the congeneric model. Also, I could completely drop this command here about the intercepts because Mplus would automatically estimate the intercepts. However, I want to keep a specification that is consistent with what we did previously. So I'm going to keep the first intercept here fixed at 0, and I'm going to freely estimate the remaining three intercepts by putting them in the same brackets and then putting a star there. So estimate intercepts. And then that way I can still estimate the latent mean of the true score variable, which is not really necessary, but it's consistent and it's okay. So say with previous models that we have estimated. So we have the true score mean, we have the true score variance again, and we also estimate all four error variances freely under this model. And so then you have your congeneric measurement model with unequal loading. So let's take a look at that model, how that fits our four variables here. Let's take a look at the chi-square. And you can see this model fits the data very well. It has 2 degrees of freedom when there are 4 variables, and the chi-square value is 0.552. The p-value is 0.7589, which indicates excellent model fit. RMSEA is 0, CFI-TLI are 1, and the SRMR is also very, very close to 0. So this is a really well-fitting model for these data. You can see that now factor loadings are allowed to differ. The first one is fixed to 1 for identification, as we would usually do in confirmatory factor analysis, and the other loadings are estimated. They are all fairly close to 1, so probably a model of essential tau equivalence would work here as well for those 4 variables, because these loadings are all so close to 1, so maybe they could all be fixed to 1 without loss in model fit, and that's something that you could test as well. We get the mean, we get the intercepts here, and the true score variance, as well as the residual variances, which are all different. And at the very end, under the standardized solution, you get your R-squared values that indicate reliability of these 4 scales, which here range from 0.585 to 0.711. They are not super high, but perhaps you would use the test in the aggregate. Those are all subscales of the same test. And then you would calculate a composite reliability coefficient for the entire sum score, such as, for example, McDonald's omega under the congeneric model. Or if you could assume essential tau equivalence, you could use Cronbach's alpha for composite reliability. And so then composite reliability for those 4 scales combined would probably be decent and would probably be above 0.8, given that these are all already relatively high. I hope you found this video useful to learn about how to fit measurement models of classical test theory in the Mplus software. If you did, then please consider subscribing to this channel, and don't forget to check out the description for additional resources, including courses on measurement theory and classical test theory that we offer through QuantFish.